Everything in hydrostatics derives from the linear relationship between pressure and the vertical distance of a point in a liquid from the free surface of the liquid, what we call the pressure head. Plotting pressure P against pressure head H, we have a straight line with gradient ρg as shown here. We often represent this as a pressure distribution with arrows representing the magnitude of the pressure at different depths. We also often dispense with the axes and represent this in the form of a pressure diagram, usually shown with arrows pointing towards the vertical face, and sometimes simply with horizontal lines representing the pressure. Suppose we have a plane surface submerged in a fluid and a rectangular area on which we want to know the hydraulic thrust. To help with visualization, we mark the line where the fluid intersects with the surface and label it OO. We know the direction of the resultant force is perpendicular to the surface, since hydrostatic pressure is perpendicular to the surface. To define the hydraulic thrust, we need to calculate its magnitude and point of application. For convenience, we adopt an alternative representation of this layout by looking at two views. One view is a projection of the surface looked at square on, in the plane of the surface as shown here. This is then combined with a side view perpendicular to the plane surface, so that our diagram looks like this. Let's remind ourselves of what the direct formula method tells us about the hydraulic thrust. If x bar is the distance of the centre of gravity of A from OO, measured in the plane of the surface, and h bar denotes the depth or pressure head at that point, then the magnitude of the thrust is given by the pressure at the centre of gravity of A, denoted g here, multiplied by the area, which is ρg h bar times A. However, the thrust does not act through the centre of gravity. Its line of action is through the centre of pressure, denoted C. The centre of pressure is the point of application of the hydraulic thrust F, which produces the same rotational momentum effect around the axis OO as the hydrostatic pressure distributed over the surface of interest. If x0 is the distance of C from OO in the plane, and h0 is the corresponding depth, then we know that x0 equals x bar plus ig over ax bar, and h0 equals h bar plus ig sine squared theta over ax bar, where ig is the second moment of area, or moment of inertia, of A about its centre of gravity, and theta is the angle between the plane and the free surface of the liquid. To unravel this further, we need the dimensions and position of area A. Let the dimensions of A be B and D as shown here, and let the top of A be a distance x1 below OO measured in the plane, with a corresponding depth h1. Let's look first at the magnitude of the thrust. The area of A is B times D, so F can be written ρg BD h bar. We also know from the geometry that h bar equals x bar times sine theta, giving us ρg BD sine theta x bar. Now let's turn our attention to the trapezoidal pressure diagram, which represents the distribution of pressure over A. Let the area of the pressure diagram be AP. The pressure at the top of A is ρg h1, and we can see from the geometry that h1 equals x1 sine theta, giving a pressure of ρg x1 sine theta, and the pressure at the bottom is ρg x1 plus d sine theta. The trapezium has a height d, thus its area is ρg d times x1 plus a half d sine theta. Now x1 plus a half d is x bar, the distance from OO to G, giving us ρg d x bar sine theta, and x bar sine theta is h bar. If we compare this to the formula for F, we can see that if we multiply the area of the pressure diagram by the width, b, we get the magnitude of the force. This gives rise to the notion of the pressure prism. We imagine a prism of pressure acting over our area A. The volume of this pressure prism is ρg BD times h bar, i.e. its volume equals the magnitude of the hydraulic thrust. It thus provides an alternative method for calculating the magnitude of the hydraulic thrust without recourse to the formula. Now let's look at the centre of pressure. The direct formula tells us that x0 equals x bar plus Ig over Ax bar, where Ig is the second moment of area of A about its centre of gravity. For a rectangle of width b and height d, this is BD cubed over 12. The area of the rectangular surface is BD, so we have x bar plus d squared over 12x bar. Let's go back to our pressure prism. What we will see is that the line of action of the hydraulic thrust goes through the centre of gravity of the pressure prism. Let Gp denote the centre of gravity of the pressure diagram, and let y bar be the distance of Gp from the top of the trapezium. We can divide the pressure diagram into a triangle and a rectangle as shown here. Let yt bar and yr bar be the centres of gravity of the triangle and rectangle respectively. The centre of gravity for a triangle is 1/3 of the height from the base, thus yt bar equals 2/3 d, and the centre of gravity for a rectangle is its midpoint, so yr bar equals 1/2 d. We already established that the trapezoidal pressure diagram has area ρg d x bar sine theta. The triangle has base length ρg d sine theta and height d, thus at equals 1/2 ρg d squared sine theta, and the rectangle has a width ρg x1 sine theta and height d, thus ar equals ρg d x1 sine theta. We now have everything we need to find the centre of gravity of the pressure diagram. We have y bar multiplied by the area of the pressure diagram, AP, is the sum of yt bar times at and yr bar times ar. Substituting first for yt bar, at, yr bar and ar, we have y bar times ap equals 2/3 d times 1/2 ρg d squared sine theta plus 1/2 d times ρg d x1 sine theta. Tidying this up and then substituting for AP yields y bar times x bar equals d times 1/3 d plus 1/2 x1. Now we can eliminate x1 from this equation by replacing it with x bar minus 1/2 d to obtain the equation y bar equals 1/2 d plus d squared over 12x bar. Going back to our inclined plane surface, we can see from the geometry that if we make an orthogonal projection of Gp onto a point P on the plane surface, then P is a distance y bar from the top of area A, and thus is a distance x1 plus y bar from OO. Given our expression for y bar, this means that P is a distance of x1 plus 1/2 d plus d squared over 12x bar from OO. We also know that x bar equals x1 plus 1/2 d, and we can see that this expression is identical to the formula for x0. Thus we have shown that the point P coincides with the centre of pressure C. The pressure diagram thus provides an alternative way of finding the centre of pressure. We now have a complete method for calculating the hydraulic thrust on plane surfaces without using the direct formula. We know the force is perpendicular to the plane, so we only need to find its magnitude and line of action. First, we look at the pressure diagram. Then we generate a pressure prism from that pressure diagram, and we know that the magnitude of the thrust, F, equals the volume of the pressure prism. Next, we find the centre of gravity, Gp, of the pressure prism, and we make an orthogonal projection from GP to a point on the plane surface. That point is the point of application of the hydraulic thrust, or centre of pressure. This method can be generalised, but finding the centre of gravity of the pressure prism can be difficult for a general shape, and it's better to use the direct formula. Thus we usually only use this method for surfaces of uniform width, in which the centre of gravity of the pressure prism is on the vertical axis of symmetry, and the position of C can be found simply by finding the centre of gravity of the pressure diagram as we have done here. Often, we have pressure diagrams that go all the way to the free surface of the fluid. In this case, the calculations are simple, since we know that the centre of gravity is halfway down the surface, and, since the centre of gravity of a triangle is 1/3 of its height from the bottom, we know that the centre of pressure will be 2/3 of the way down the surface. If we look at the pressure diagram in this case, it's a triangle, with base length ρg d sine theta and height d. The magnitude of the force is the volume of the pressure prism, so F equals 1/2 ρg d sine theta times d times the width b, which equals 1/2 ρg b d squared sine theta. The line of action of the force will be at a depth of 2/3 of h, i.e. 2/3 times d sine theta. Let's look at an example. We have a rectangular plate submerged in water, lying on a plane surface at an angle of 60 degrees to the horizontal. The plate has dimensions 10.4 meters by 5 meters, and we want to find the hydraulic thrust on the plate. We'll have a pressure diagram like this. We need to find the length of the base of the pressure diagram, which is ρg times the depth of the bottom of the plate. Let the depth of the bottom of the plate be denoted h. We get 10.4 times sine of 60 degrees, which is 9 meters. Taking the density of water to be 1000 kilograms per meters cubed, we have the pressure at the bottom equals 88,290 pascals. The magnitude of the thrust is the volume of the pressure prism, which is half base times the height times the width, giving us 2,296 kilonewtons. Finally, the centre of pressure is a depth of 2/3 of h, which is 6 meters. Remember, this method is applicable to areas of uniform width only. It gives both the distribution of load and the total force. It can be used to determine the hydraulic thrust on curved surfaces as well as plane surfaces, and we'll look at that in another video.